Hi all, so here's another video I made in my machine learning journey where I have been attempting to get a high to, I want to say on the low end of a intermediate level knowledge, understanding of machine learning, deep learning, and what it can do for someone with a background in programming, full stack development, some cloud, things of that nature. I don't claim to be a data scientist, so that's my disclaimer. I'm not even remotely close to being a data scientist. This is all fairly new to me, but I will say in the last probably 6 to 8 weeks, I've been kind of doing a dive into it, and I'm going to give a kind of credit and a thumbs up to this particular course that you're seeing right here. This is where I got a lot of the knowledge that I'm learning, and I can't recommend it enough. And again, the folks in this who created this course have been very kind to give me permission and such to show you some of the content, but I'm making a conscious effort to not show you too much of it so that you won't feel like you don't need to buy the course. So that's just my way of, out of respect for the folks who created this course and all the incredibly hard work that they've done to put this together. So it is highly worthwhile. So based on this, I kind of wanted to cover or kind of go over or demo another thing that they had talked about, which is XGBoost and boosting algorithms. So the long and short of it, as far as what boosting algorithms are and what they do, is they refer to a family of algorithms that convert weak learners to strong learners. And as far as, what is a weak learner and what is a strong learner, one of the examples given that I saw was the concept of determining whether an email that you get is a spam or not a spam. So as far as that goes, there's many different ways, rules and such that may or may not qualify an email as spam. One of them may be if you get an email that has all kinds of links, hyperlinks to it, things of that nature, potentially, that rule itself can be considered, yeah, it's pretty much a spam for the most part. Another one is if you get an email and there's some content in there that says you won. So the algorithm and such would actually interrogate the body and find certain keywords that say you won and pretty much determine nobody, none of your friends and family and such would say something like you won a prize, so that would be another rule that could potentially be determined as spam. Another one would be if you get an email that is from a known domain. In those cases, that could be something you subscribe to, a newsletter, things of that nature. So that could be tagged as not a spam. Each of those rules unto themselves would be considered a weak learner. And the whole concept in boosting where you're converting a weak learner, a bunch of weak learners to a strong learner, if you combine all of those rules together, the likelihood of all of those rules combined together would give you a strong learner. So again, it's that whole concept with decision trees where we talked about ensembles. A single decision tree on its own may not be as powerful as an ensemble or a random forest of decision trees. So that whole concept is based on the power of the crowd. So this is the same thing with weak and strong learners. So the idea is to take several weak learners, which might be rules unto themselves that you're sort of trying to classify as a spam or not a spam. And if you combine them all together and do things like whether you average them or you sum up the pluses and minuses and do the majority rule things, whereas if you have more pluses, then that would indicate the classification is true. If you don't have more pluses, then that would be the classification is false. So in a way, that's kind of what boosting is. And as far as how that works to find the weak rules, so you're going to apply base learning algorithms to different distributions. So each time, the base learning algorithm is applied, it's going to generate a new prediction weak rule. And you go through this many iterations. Fortunately, the algorithms themselves will do this for you, but the boosting algorithm combines all these weak rules into a single strong prediction rule. Again, the power of the crowd. So for the most part, there are several different types of algorithms for boosting. One is the XGBoost, and then the other is going to be the decision tree boost. And as far as, they pretty much give you the end result, but they do things a little bit differently. So with the XGBoost, that's known as the weak rule, strong rule, stuff that I just talked to you about with the spamming. Now you have a whole other family of boosting algorithm, which is a decision tree boost. And recently there's a popular open source library called XGBoost, which is based on the decision tree algorithm. So gradient boosting, again, that's the gradient tree boosting for XGBoost. And that's, like I said, that's typically used with decision trees of a fixed size as your base learners. Whereas with the XGBoost, you've got your different rules as your base learners that I had talked about earlier. So the XGBoost apparently in recent times has become increasingly more and more popular as far as doing these families of predictions for your neural networks and things of that nature. And you may ask yourself, what's so special about that? I did the same thing myself. And the reality of the matter is that they run so much faster, almost instantaneous on large data sets. And the models that they generate is very, very efficient. And they're just as accurate as the decision trees and ensembles and things of that nature. So I was just going to kind of give you a demonstration on this using one of the labs that we worked with. And again, for the integrity and respect, I'm not going to include a lot of the stuff that I documented. So I'll just include some of the raw examples that they shown in hopes that you'll consider buying the course if you want to dig deeper into this, because it's really a good course. So again, XGBoost is the most powerful implementation of the gradient descent of model performance and execution speed. In order to use XGBoost, though, it doesn't come out of the box with your Anaconda/Spider installation. So you'll actually have to install XGBoost. You can do a Google search. In my case, I have a Windows environment, and here's the instructions on what I had to do to install XGBoost. The course itself gave some instructions on it, but I found that those instructions didn't work. I'm not sure if that's because a little bit of that was outdated or what have you, but after some searching, this particular site is what gave me the best results on installing XGBoost in Windows. So I'm not going to really go over this. I went through the installation. The key, though, is after you go through these instructions, and again, you can use that link, you'll have to shut down your Anaconda and Spider and then restart it again. And then you'll have XGBoost available to you inside of your environment. So going through the algorithm and stuff in the problem, this particular problem was done in a previous lab. So, and that lab was using, kind of like the trees and such. And although that particular lab generated an accuracy of 86%, which for this particular problem is a very well-respected, pretty much the best you're going to get in this particular case. Again, with machine learning, there is no perfect model, but there are some models that perform better than others. And in many cases, a 70% accuracy rating may be considered optimal and something that a company considers investing a lot of money into building an engine that'll give you 70%. It's one of the key things for me about learning machine learning is you don't always, it's unrealistic to always strive for like a 90%, 95, 97% rating, although that's great and awesome. And there are cases where you can get that level of accuracy with your predictions. There are just other types of business problems that naturally may yield, even in some cases, a 60, 70% at best. And in those cases, it's still worth a company's investment in applying models and such to their business practices. because every little bit helps, especially when you're trying to get the edge over your competition and things of that nature. So anyhow, this given example is all about predicting the customers at the bank who will leave and not leave the bank. It's not my example that I turned up or whatever. It's a part of the lab. If you take the course, you will actually see. What I want to do is just create this data set so that I can get a better representation of what that data set looks like to you. And again, this was done in a previous lab with decision trees and such, and we got an 86%. It took a while to run those. So the whole purpose of XGBoost is, hey, can we pretty much achieve the same results in a fraction of the time? And so that's what this demo will show you. So here's pretty much our data set. If you look at the very end, here's the exited. So you get 1 or 0 indicating whether or not the customer is going to ultimately leave or stay with the bank. And this is technically supposed to be based on real live data. Now this is just a test data set. I mean, it's not real live data, then it's all pure coincidence. But in reality, if you're working on a problem like this in real life, you want to get real live data historically. And these are all the different characteristics or features, as they call, like age and all that kind of stuff. So based on all of these characteristics, over time, the customer ended up either staying or leaving the bank. So that's the purpose of it, is we want to create an engine that'll make predictions with new customers with similar types of features and all that. And we'll see if the XGBoost algorithm can actually give us better performance on that. So we've imported the database. One other key thing that I didn't really mention in the past is the idea of dummy variables. And I find dummy variables to be quite interesting. And they're more than just dummy variables. But in a nutshell, if you look at the original data set coming in, you're going to see things like gender, which is coming in as a female or a male. You're also going to see something like the geography, which if you notice is France, Spain, Germany. There's just a few results inside of here. This is coming in as text. And everything done with machine learning, calculations and predictions has to be done on numbers. So there's really no easy way to do these calculations based on strings. So what you have to do is categorize these, or create categories out of the gender column as well as the geography. You have to turn them into numbers. So one way is a female could be a 1 and then a male could be a 0. And the other key important thing to note is that just the number 1 is not always greater than the number 0 in these cases, because these categorizations do not actually have weight in terms of priority or in terms of one being greater than the other. So in the case of geography, we may turn France into 0, Spain into 1, and Germany into 2. But that does not mean that 2 is greater than 1 in this case, or that 1 is greater than 0. They're just categories represented by a number. So that concept of turning these strings into numbers is known as creating dummy variables. So that's what you have libraries of, like one-hot encoders to do, things of that nature. So if you take a look right here, what we've done here is we've turned our data set now, with the geography and the gender, we've turned that now into categories. So if you take a look at right here, the gender column right here of 3 is basically going to be male or female, depending on 1 or 0. And then if you take a look at the geography columns and such like that, what you're going to get is, in this case, you have 3 possible values: France, Spain, and Germany. We end up with 2 columns. And so like where one of these columns would be France if the value is 1, the other one would be Germany here if the value is 1. If it's not Germany, then the value is 0. And so the next question you might be asking is, well, where the heck did Spain go? And the whole idea behind that, and it's kind of unrelated to XGBoost, but I just wanted to mention it right away, is there's a thing called the dummy variable trap. And there's explanations out there about the dummy variable trap and how to prevent that from skewing up your, shall we say, your predictions and your data. But there's mathematical reasoning behind it. And again, you don't really have to understand the pure mathematics behind it if you're not a data scientist like myself. If you just want to be an application developer, or if you're just starting out on this. The key thing to take away, though, is in order to alleviate the dummy variable trap, which is going to potentially influence your predictions in a way that you don't want to do, the dummy variable trap is remedied by eliminating one of the dummy variables. So instead of 3 possible cases right here for the geography, you're going to have 2. Instead of 2 possible cases for the gender, you're going to have 1. And the concept is, if you have all 3 variables, you can potentially predict the value of one of them based on the other 2. So there is redundancy. And also in the concept of gender, you can pretty much infer that with one column, you can identify both. So in one column, if you have a 1 here for whether it's female, then you pretty much know a 0 here implies that the other one is a male. So you really don't want to include both of those columns in your data set, because again, it will skew up your results in your model. And so that, in a nutshell, is what the dummy variable is and the whole dummy variable trap. So sorry for that digression, but it's a very important concept, and I just kind of wanted to run that by you. So now what we want to do, going back to this example using XGBoost, and again, we've installed XGBoost. We're going to split our training and our test set. And what we've done here is we just basically, by giving it a test size of 0.2, that implies we want a training size of 0.8. So we're taking our full data set of 10,000 entries. Now we've got our X train and our Y train, which basically have 8,000 entries. So that's our training set that we're going to go ahead and train the model with. And our test set, after we've trained the model, is going to have the other 2,000 entries, as you can see right here, as long as with your Y test. There we go. So there's your 2,000 there. So we've accomplished that. Now what we want to do is use the Xgb Classifier, and that's a part of the XGBoost library. And so if I do like let me try doing something here, if I can, the help on this, I'm trying to do a Command I here to try to get the help text to show up. Unfortunately, it doesn't in this case. That's one of the problems with the open source thing. It doesn't always do it. But please know, by default, this XGB classifier, since it's based on gradient tree boosting, by default, it is going to have 100 trees, 100 decision trees. So if we go ahead and run XGBoost, watch how fast this takes to train our model. So it was very fast right there. Whereas with the other algorithm in the past, it would take a much, much, much longer time. The N estimators in the output basically is the default of 100 decision trees that we're using behind the scenes. And you can do more research on some of these. We had talked about kind of like the learning rate, some of these other things, that these are all configurable as parameters based on what you supply as your argument to the Xgb classifier. We're using the defaults here. So now, based on that, we have fitted XGBoost to our training set. And now we actually want to do the results on our X test. So what is our X test? That's our 2,000 other data rows right here from our data set that were not included as a part of training the model. So let's go ahead and run that prediction. And again, watch how fast that occurred. You can see it was like lightning fast. And so there's our results. So we actually want to take a look at our X train. our X test. And if we mirror it up, here's our prediction for this. So you got zeros or 1 for they will leave the bank, 0 for they won't leave the bank. So one of the keys here in working with the previous lab, it had an 86% accuracy with the decision trees using the random forest and stuff like that. That's about as best as you're going to get in this type of a business problem, as they clearly stated in the course. So what we really want to do, now that we're using a totally different algorithm with XGBoost, how accurate is that? So what we can do is we have a couple of ways to do this. We're gonna take a look at our confusion matrix, which basically generates a tree of accuracies. So you do that by going diagonally. So this is like this column here is how many predictions our model said that they would stay, and then here's how many predictions our model said that they would leave. And then going vertically, then going horizontally, this is how many actually stayed. How many actually stayed and how many actually left. I'm kind of getting confused by the 0 and 1. 0 basically means they stayed, and 1 means they left. And then here, these are how many, actually ended up staying and how many ended up leaving. So to figure out the accuracy of that, you would go diagonally by saying 1521 plus 208, because again, we're going diagonally with the prediction plus the actual. And then we want to divide it by the total number of rows in our set, which is 2000. Whoops, what have we got going on here? So we want to say 1521 plus 208 gives us 1729, and we want to divide it by 2000. That comes up with an accuracy rating of 86%. So that's approximately the same as our previous lab that took a long time to run not using XGBoost. So this is pretty much demonstrating the value of the XGBoost algorithm. Now the other thing we can do is, I didn't mention this before, and I may do another video on that this course also discussed, is the whole concept of k-fold cross-validation. And that is another technique and a measure of, measuring the accuracy of your different algorithms and your different models. So k-fold doesn't necessarily apply to XGBoost, but what you do with k-fold is you can have it evaluate the accuracy of your model. So what you end up doing is you compute the k-fold validation on different training and test folds, if you will. So those are iterations internally behind the scenes that the k-fold validation goes and creates. And so it's a lot of randomness going on here. By the CV10, that just basically means we want 10 samplings, 10 accuracies, and 10 folds. And what happens is it's going to take the mean and standard deviation of those 10. So this is configurable. And so this is another technique worth looking into, just to say how accurate was our model and such. So right now, as you can see, I'm running that right here. Takes a little bit of time to run that finished. Now what we can do is we can say, what was the mean of all 10 of those? And lo and behold, we get 86%. So 86.2, which pretty much is on par with our previous lab that took forever to run, not forever, but took a lot longer to run with the decision tree random forest and things of that nature. Now, I'm not knocking decision tree random forest. Those are very useful and extremely good algorithms too. This is just another means, another open source, algorithm that more and more data scientists out there are starting to check out, particularly with the eta boosting, which is the weak and strong classifiers boosting, as well as the gradient tree boosting, which is what XGBoost is based on. Now, the last thing you can do with the accuracies is you can check out the standard deviation. And what this strange looking number basically means is 1%. So what you're saying, what does that mean, 1%? Well, being that our mean is 86% and our standard deviation is about 1%, that pretty much means that you will get either between 85% or 87% precision accuracy on this model that we had just generated with XGBoost, again, which is right on par with, you know, doing the random forest ensemble. So that 85 and 87% that you'll get just basically means, you know, if our mean is 86% and our standard deviation is 1%, that just means plus or minus 1% from our mean. So in the long and short of it, XGBoost is apparently an up-and-coming trend in the industry for data science, and it's definitely something you're probably going to see more and more used going forward in the future. I hope this helped. Again, the course rocks. I don't want to take any credit for any of the content in here. That belongs to the folks that created that course. Also, I don't want to take any credit for quote unquote claiming to say I know this stuff. I'm learning a lot more about it, but I'm giving 100% credit for the folks that created the course. And I thank them truly for allowing me permission to show you some of this, share this, as well as for the knowledge that they have given me from the course. So thanks again, everybody. I hope you have a great one, and I hope, you know, some of these videos help other fellow coders out there, such as myself, who wanted to learn a little bit more about machine learning and deep learning and what it can provide for you. So have a great day. Bye-bye.